Yes, so today it's my pleasure to present private access control for function secret sharing. This is joint work with 3 high school students that I mentored through the MIT Primes program. So to start with some background, what is secret sharing? So secret sharing, as we're probably all familiar in this room, is a way of splitting a value into multiple shares such that the shares could be recombined to recover the value. And strict subsets of shares reveal nothing about the secret. And we will use bracket notation to indicate the ith share of a value v, and add addition for recombining shares. So if we have 2 secret shares, we can add them together and get back the value. Function secret sharing applies the same idea, but to functions. So in addition to being able to secret share a function f, the idea is that you can also evaluate a party holding a secret share of f can evaluate the function to obtain a secret share of f of x non-interactively for any x in the domain. And so the main property that function secret sharing has to satisfy is that the actual shares of f are succinct, so much smaller than the truth table of f. And like with secret sharing, I'll use bracket notation to denote the ith secret share of f, and f of x in brackets to denote the evaluation of f on an input x. And recombining will be done, will be denoted the same way. So why is FSS useful? Well, suppose a user wants to run a function on some data stored in the cloud, but doesn't want to reveal this function to the servers, the cloud servers. One solution is to assume non-collusion between the cloud servers and use FSS to secret share the function between these servers so that they don't learn what function they're computing on. So one way this might look or be used in practice is to have the user send FSS secret shares of a function f to the cloud servers. The cloud servers then run this function on some data x and send back the secret shares to the user, who can then recombine the shares to get f of x, the output. So visually what this looks like is we have a user here who I'll also call the dealer, who can secret share the function with the 2 servers, for example. The servers then have shares of this function, and they can compute it evaluate the function on some input x known to both servers, and then obtain secret shares of f of x non-interactively. And then they can send back these shares to the user, who can then recombine and get f of x locally. So in this paper, we look at access control for FSS. So why do we want to look at this problem? So in many systems where FSS is deployed, there are many users. And it's natural to assume that some of these users might have different access rights. So some users might be able to evaluate functions that other users cannot. And so we develop access control for FSS. The function evaluators can make sure that whoever sent the shares of the function f has access rights to this function. So for example, some users might have access to a function foo, whereas other users might have access to a function bar. And the evaluators cannot distinguish between shares of foo and shares of bar. And so this makes it kind of challenging to apply access control, because the evaluators themselves do not know what function they have secret shares of. And so in some sense, this is in fundamental conflict with access control. And so some applications of access control for FSS include private information retrieval with access control. So for example, if you have a setting where some users have access to some database records, whereas other users have access to other database records, access control for FSS can enable enforcing access rights over the database. Another application that is really useful in anonymous communication systems is private information writing. And in this setting, access control can be useful to prevent malicious users from jamming mailboxes that belong to other users in the system. And so, yeah, in anonymous communication protocols, this can be really useful. And a third application is anonymous authentication, so proving that a user has a valid account without revealing what account belongs to the user. So an example of this might be a student at a university, and so a university might only want to allow students and faculty to access a building, but students do not want to reveal their identity to the university. So how do we model access control for FSS? We introduced the notion of private access control lists, or PACLs. The goal is to have that an access key alpha will give access to a function f. And authenticating with the access key alpha does not reveal anything about the function f, because we want to ensure that the privacy property of FSS is preserved. And so if you don't know the access key alpha, you shouldn't be able to share secreture f with the evaluators. Of course, because in FSS we won't have one function, instead we have a family of functions. We'll also have a list of access keys, so VK1 through VKN, and I'll call this the access control list, such that each verification key I is associated with the function I in the family of functions. So again, visually, here we have the user that will secreture the function as before, but now the user will also send secretures of a proof pi. And so this proof will essentially say that the user has access or knows the correct access key for the function that is being secretured. So when the servers have the shares of the function and the proof, they can run a lightweight protocol to, along with the verification keys, to check that the user actually has the corresponding access key for the function that is secretured. And if this protocol outputs OK, then the servers know that the user actually has the right access key for the function f. And so the main building block we focus on in the paper is access control for distributed point functions, or DPFs. Point functions are functions that evaluate to 1 on some index, on input j, and evaluate to 0 on all other inputs. Another way to think of these functions is as a one-hot vector, because if you evaluate the function on the entire domain, you'll get 0 everywhere except at the jth index. And in prior work, it has been shown that distributed point functions enable function secret sharing for more complex functions. And in our paper, we show that access control for DPFs enables access control for a larger class of FSS. So how do we construct PACLs for distributed point functions? We will start with a group G and a little generator G. And we will assign to the jth point function the access key alpha j and verification key g to the alpha j. So if you look at all the point functions in the family, you would have g to the alpha 1 all the way to g to the alpha n, where there's n point functions in the family of functions. And then a dealer that is authorized to share point function j will have access key skj equals to alpha j. And so on the right here, you can see we have each point function and the associated verification key of that point function. So then the protocol itself is very simple. The dealer secretures the proof pi, where pi is just minus alpha j. The evaluators then will use the point function pj to expand it into this one-hot vector representation, but recall that it's secretured, so now they have a secretured one-hot vector. And then they can take the inner product in the exponent to derive multiplicative shares of the verification key g to the alpha j, where alpha j is the function, is the verification key associated with the point function pj. Then the evaluators proceed to compute an audit token, which will just consist of the product between the verification, multiplicative shares of the verification key that they derived in step 2 with the exponentiation of g to the secreture of the proof provided by the prover. Then they swap all these audit tokens and check that the audit tokens recover to the identity element in the group. So to quickly analyze security of this protocol, we have completeness because if the proof pi is actually minus alpha j, then you recover g to the 0. And so this holds. proof of knowledge holds because from the proof shares, you can recover the discrete log of the verification key. And zero knowledge holds because the user sends secret shares of the proof pi, which can be efficiently simulated, and the audit tokens are always going to be the identity element when the prover is honest. And so they can be simulated efficiently as well. So in the paper, we provide more details. We show how to model access control under different threat models with like secret access key, access control lists, and public key access control lists. We construct more efficient pack calls and discuss other concrete optimizations. And we construct generic pack calls for any FSS scheme, not just distributed point functions and related functions. So now I'll just quickly go over a couple applications of pack calls. So the first one is private information retrieval with access control. So we find that when you apply pack calls to private information retrieval, there's about a 1.5 to 3x overhead over just doing PIR with FSS. But the overhead diminishes as the records get larger and stays the same as you increase the number of records in the database. And then another application is for anonymous communication, where we show that pack calls can be used to in two anonymous communication systems, Express and Spectrum, and replacing the access control mechanisms that exist in those papers, in those schemes, can reduce the concrete overhead on the servers by up to 70x when the number of mailboxes becomes very large. So with that, I'll take questions.
Thanks for the great talk. I have a more fundamental question. If you use DPFs, right, the way they are typically run on servers is that they evaluate the DPF pointwise. Mm-hmm. So if the servers already know the access control matrix corresponding to each client, can they not just not evaluate it on the points that the client doesn't have access to? And you don't really need any information from the clients. Everything that you need is already at the servers.
So no, because I think you're right that they could evaluate it just point-wise, and actually pack calls apply to point-wise evaluations as well. But the problem there is that the servers will not be able to know what function was secret shared, right? They don't know the function. Even if they evaluate it point-wise, they don't know what the function is because it's secret shared.
But you don't really. Okay, maybe for some more expressive functions that might be useful, but it seems like for many use cases, for the peer example and other use cases, you don't really need something this heavyweight. You can just not evaluate it on points that the client doesn't have access to, and that should...
Not exactly, because then you wouldn't need FSS, actually, because you could just the servers could just have the function in the clear.
No, let's say that there's an alpha, right? And let's say this alpha is from, the range is like 1 to 100, and alpha is, let's say, 5. And let's say the client only has access to the first 10 entries of the database, not the other entries. Mm-hmm. And the server can just run their key on the first 10 entries. The server still doesn't know that it was 5 that the client requested, but then they don't really need to evaluate.
So in that case, yes. Yeah.
Mm-hmm.
I was just wondering, can you have more expressive access control specification, not just for every single point you have a key, especially if you go to general FSS, that's not point functions, maybe in that context? I'm not sure whether access control is always per point necessarily. Yeah,
so here we specifically associate a key with the function, so it would be, even if you have more complex functions, you can still have a key. In the paper, we show how you can have multiple keys per function, so then you can, instead of just proving that you know one key, you prove that you know a key from a set of keys that corresponds to a function.
Okay. All right. Thank you very much.
Thank you.